Hello everyone. Welcome to the fourth lecture of the series on deep learning for control. In this lecture, we will discuss about autoencoders, which comes under unsupervised learning. We start with the problem of dimensionality reduction and the principal component analysis or PCA, which is a linear dimensionality reduction method. Then we move on to autoencoder or AE, which can be considered as a nonlinear dimensionality reduction approach or a nonlinear extension of PCA. Then we discuss the autoencoder with ordered variants, in which the latent variables are ordered according to their variants, similar to PCA. In general, real-world high-dimensional data is likely to concentrate in the neighborhood of low-dimensional manifolds. This is also known as the unsupervised learning hypothesis, and this resulted in a subfield of unsupervised learning known as dimensionality reduction. Here by manifold, we means a nonlinear curve, and if the data lies in a lower dimensional manifold, we have the possibility of dimensionality reduction. Two of the major problems in dimensionality reduction are the feature extraction, in which the objective is to extract lower dimensional features from the high dimensional dataset, and the model extraction, which deals with identifying the relationships amongst the variables in the dataset. Autoencoder is a deep learning model which is commonly used for dimensionality reduction. It can be considered as a nonlinear extension of the principal component analysis or PCA. PCA is a linear dimensionality reduction method in which we consider an input data or the unlabeled data as in equation 1, which consists of capital D samples of the vector x, where x1, x2, xd denote samples of the dataset. And each sample is considered to be a n-dimensional vector, which means we have n variables and these samples. Since PCI is an unsupervised learning method, we consider there is no labels available. In other words, all the available information consists of this data set, which we can also call as the input data to the PCA model. We can also define the latent and reconstructed data as in equation 2, where this y contains the latent vectors, which are denoted by y1, y2 till yd, and this x hat matrix contains the reconstructed input vectors. Now in PCA, the dimensionality reduction is achieved by using a linear transformation as in equation 3, where this transformation matrix P transforms the input vector x to a latent vector y, where y contains small m number of variables and x contains n variables. In general, m is less than or equal to n, and in the case of dimensionality reduction, we will be having m is strictly less than n. From y, the reconstructed input can be computed as in equation 4. Then the optimization problem for PCA is to find the optimal transformation matrix P, which minimizes the reconstruction error, where the reconstruction error is the error between x and x hat. And also we have constraint, which means like the P matrix should be orthogonal, or in other words, P transpose P should be equal to identity matrix. In figure 1, we can have a pictorial representation of PCA, where we have the input vector x is transformed into a latent vector y using a linear transformation P transpose. And from y, we can reconstruct the input x hat using the inverse transformation, which is P. Since P is orthogonal, P transpose will be P inverse. Now, PCI is particularly useful for dimensionality reduction if the original data contains linear relationships. Or in other words, if the data set is oriented along a lower dimensional hyperplane, as shown in this figure, where we consider a two-dimensional data containing small letter x1 and small letter x2 as the variables of the data set. And here we can see different samples. X1 is the first sample, x2 is the second sample, and so on. Here the data set is mostly oriented along this red line as shown in this figure. Now, if we consider a linear transformation or like a coordinate transformation with the P1 and P2, we can see that most of the data is aligned along P1 and the variance of the data along P2 is small. If we consider y2 as the coordinate of this data along P2 and y1 as the coordinate of this data along P1, we can see that variance of y1 will be more because the data is spread across P1. The variance of y2 will be small, or let's say nearly 0, because the data is not varying much along P2. This means the variance of the data in the direction of P2 is small. In other words, variance of y2 is small. And in this case, if we consider the variance of y2 as approximately 0, then we will be having P2 transpose X equal to 0, which gives a linear relationship. In the case of model extraction, we can select the number of latent variables n equal to the number of input variables m itself. And then based on the latent variances, we can split the latent variables into principal and residual variables, where the principal variables consist of the first p variables, which has significant variance, and the residual variables consist of the remaining n minus p variables, which has negligible variance, or like the variance is nearly 0. This distinction between principal and residual variables can be achieved by introducing a threshold for the latent variance, and this threshold can be chosen nearly 0. And all the variables with the variance greater than the threshold are considered as principal variables, and all the latent variables with the variances less than the threshold are considered as residual variables. Now, since the residual variables have 0 mean and variance, we can have YR can be equal to 0. And if we substitute this condition in this equation, we will be having PR transpose X will be equal to 0, which gives us a linear relationship. In this figure, we can have a schematic representation of the model extraction using PCA, where we have the input data X is there, which is an unlabeled data, and we are transforming it into a latent space using a transformation matrix P, which we can split it into principal and residual part, where PP is the principal component and PR is the residual component. This part will basically give the latent variables with significant variance, which can also consider as the features or linear combinations that capture most of the information in the original data set. Therefore, this principal component part can be used for feature extraction. And when it comes to these residual variables, these variables are having negligible or like nearly 0 variance. Since the original data is assumed to be mean-centered, we have these latent variables will be having 0 mean and 0 variance, which gives us YR equal to 0 or PR transpose X equal to 0, which gives a linear model in an unsupervised setting. Now, from the principal variables with the significant variance, we can reconstruct the data set using the inverse transformation, which gives us the reconstructed input. To summarize, the principal components can be used for feature extraction, and the residual components can be used for model extraction. Next, we move on to autoencoder, in which we will replace the linear transformations in PCA using a nonlinear transformation with neural networks. Autoencoder is an unsupervised learning algorithm which can be used for feature extraction, where the objective is to extract lower dimensional features from the input data set. And in autoencoder, we will be focusing on nonlinear feature extraction. Autoencoders can also be used for model extraction, where the objective is to identify the relationships amongst the variables in the dataset. In general, an autoencoder consists of an encoder and decoder functions, which can be represented as in equation 9, where the latent vector is obtained by applying the encoder transformation to the input data, and the reconstructed input is obtained by applying the decoder transformation into the latent vector. And theta E and theta D consist of the parameters of the encoder and decoder network, which are the weights and biases of all the layers. Now, the optimization problem for AE is to find the optimal values of the parameters theta E and theta D, which minimizes the reconstruction error. Here is a schematic representation of the autoencoder, where we have the encoder transforms the original vector X into a latent vector Y, and the decoder reconstructs the input vector or the unlabeled vector from the latent vector. Autoencoders are suitable for dimensionality reduction if there are nonlinear relationships in the dataset. Or in other words, we have the data is oriented along a nonlinear curve as shown in this figure. So here we have this x1, x2, all these are the samples in the dataset. And here it should be xd instead of xn, since we have d samples in the dataset. Next, we briefly discuss the different variants of autoencoder, which are variational autoencoder, which uses a variational bias term in the loss function as a regularization term. And the other versions are stacked autoencoder, which is made of multiple layers of the autoencoders connected sequentially. Sparse autoencoder, which uses a sparsity-based regularization term to promote sparsity in the latent space. And then denoising autoencoder, which is commonly used for removing noise from the data. Contractive autoencoder, which uses a regularization term to constrain the latent vectors into a lower dimensional manifold. neural component analysis, which combines PCA and autoencoder. Orthogonal autoencoder, which modifies the loss function to enforce orthogonality in the latent space. And autoencoder with ordered variance, in which a variance regularization term is used for ordering the latent variables in terms of decreasing variance. Next, we move on to the autoencoder with ordered variance, or AEO, in which the encoder and decoder functions are chosen similar to the standard autoencoder. And here we have encoder consists of L number of layers and the decoder consists of H number of layers. And each layer of the encoder and decoder can be represented as a composite function similar to a neural network, as in equation 12, where sigma I contains the activation function for the ith layer, AI is the weight matrix for the ith layer, and BI is the bias vector. In the standard autoencoder, we have the loss function will be containing only the reconstruction error term. But here we have included an additional regularization term to the loss function. Now this modified loss function contains of a reconstruction error term, which is denoted by Jx, and a variance regularization term, which is denoted by Jy, and a parameter regularization term, which is denoted by J theta. This variance regularization term, we can expand it as a linear combination of the latent variances. In other words, it will be proportional to Q1 into variance of first latent variable, Q2 into variance of second latent variable, and Qm into variance of mth latent variable. If we are selecting Q1, Q2, and Qm in an increasing order, we can obtain latent variables with decreasing variances. This is the central idea of AEO. And we have the optimization problem for AEO is to find the optimal parameters theta, which minimizes the loss function. Next, we move on to the model identification using AEO, where we will extract a nonlinear model using the residual variables similar to PCA. Let us consider the encoder and decoder output layers are chosen as linear, and this simplifies the latent vector and reconstructor vector for AEO as in equation 15, where we have a linear output layer in the encoder and also a linear output layer in the decoder. Since the latent variables are ordered in decreasing variance, we can arrange the latent variables as principal variables, which is consist of the significant variances, and also the residual variables, which consist of nearly zero variance. Let's say the first p variables having significant variance, and the remaining n minus p variables are having a nearly zero variance. Then we can also split the weight matrix for the output layer of encoder as the principal part and also the residual part. If we consider the variance of the residual variables to be zero, in other words, VYR is equal to 0, which implies YR will be equal to YR bar. Since the variance of YR is 0, YR will be equal to a constant vector, which is equal to the mean value of YR. Now from this equation, we have YR will be equal to ALR times this part, and we have YR equal to YR bar. From these two conditions, we have this function minus YR bar will be equal to 0, which gives us a nonlinear model in an implicit form. We have YP will be having the significant variance, which can be used for feature extraction, and EP is the part of the encoder, which is used for feature extraction. Similarly, for YR or the residual variables, we have the variances is 0, which means like YR will be equal to YR bar at each time instant, which gives us ER of X minus YR bar equal to 0 as the nonlinear model. And from the principal variables, we can reconstruct the data using the decoder, which gives us the reconstructed input as shown here. Now, in the case of AEO, we can prove that the latent variance be arranged in decreasing order of variance. And for that, we can use a rearrangement inequality, which says that if we have two sequences arranged in non-decreasing order, then the product will be maximum if they are multiplying them in the same order. In other words, if both are in increasing direction, and if the product will be minimum if one is in increasing direction and another one is in decreasing direction. This is like C1 into Dn, C2 into Dn minus 1, and so on. And in that case, the product will be minimum. Now, using the rearrangement inequality, we can prove that if we select the Q1, Q2 in an increasing order, we will obtain the latent variances in a decreasing order for the optimal solution. Next, we move on to numerical illustration of the autoencoder with ordered variance. Here we consider a dataset containing 5 variables, which contains two nonlinear relationships as shown in equation 20. where the nonlinear relationships are defined using sine and tan function. And here we consider AEO, for which the number of layers in the encoder is chosen as 2 and in decoder also chosen as 2. And the number of neurons in the first hidden layer is chosen as 5. And the number of data samples is 200. And the hyperparameters are chosen as shown in here. And with this, we identified a model using AEO, which can be as shown in equation 22. Here we can see the comparison with PCA, where if we use PCA in this case, we obtain latent variances as shown in here, where we can see that the variances are ordered in decreasing value, but for all the 5 variables, the latent variances are non-zero. In the standard autoencoder, the latent variances are non-ordered, which we can see from here, and it is also non-zero for all the cases. Whereas in the case of AEO, we can see that the latent variances are ordered in decreasing manner, and we have for the last 2 variables, the variance is 0. Now here we can compare the model extraction performance. Here we extracted a linear model using PCA, and here we extracted a nonlinear model using autoencoder. We can see that the AEO has the best performance in terms of mean square error. Here we can see a pictorial representation of the model extraction, where the red color denotes the original data, and the blue curve shows the data predicted using the AEO model, and the green color shows the data predicted using a PCA model. Here we plotted x1 versus x4, and we have seen that in the original data set, x4 is equal to sine of 3x1, where we can see a sinusoidal curve. With PCA-based model, we obtained a linear approximation of this curve. In other words, we can say PCA can only extract linear relationships in the data. Whereas with AEO, we are obtaining a nonlinear prediction, and it is able to capture the nonlinear behavior in the dataset. This means that in the case of dataset containing large number of nonlinear relationships, AEO is a good choice for model extraction. With that, we come to the end of this lecture. Thanks for watching.